Yeah, as I've already been introduced, I'm Mathew McMaster. I'm a PhD student at Queen's University in Belfast. And today I'm going to give a very brief and qualitative look at some of the current work that we're doing with the group. And the title of my talk is Tuneable Low Magnetostrictive Nickel Iron Multilayers for high frequency application. So in high frequency applications such as reader shields in magnetic recording, it is desirable to have a material that exhibits certain properties such as a high saturation, magnetization, high permeability, near zero magnetostriction. Now, nickel iron is generally the material that we've come across being used in this application, and the quasi-static properties have been very extensively studied in the past. But the ternary diagram I show here doesn't include the high frequency parameters such as permeability and damping. So the work of some of our research group is really to expand this diagram to account for these missing parameters. So we use VNA FMR to probe the dynamic properties. Now, before we get on to looking at some of the multi-layers that we've been studying, it's worthwhile just briefly introducing what a single layer of these alloys look like. So for this, I've been using a permalloy sample, 100 nanometers, and I've been comparing it with a nickel 20 iron 80 sample, same thickness. And we can see here that the FCC permalloy is given a very well-defined FMR signal, but it does have a lower magnetization compared to the BCC iron-rich film. However, the BCC iron-rich film doesn't give a strong signal, but it does have an increased resonant frequency. So really the motivation for this part of our work is that we want the best of both worlds. We want to have this high magnetization and high resonant frequency that the iron-rich alloys are offering, but we also want that non-zero magnetostriction and that very strong, well-defined FMR signal that the permalloy is given. So we've been looking at layering the two together. We've used previous magnetostriction studies that have taken place in our group that have shown that we can alter the magnetostriction by varying thicknesses of the layers, by varying the compositions. So we've been using that as really the baseline for what we're doing on the FMR. So the first thing that we looked at was what happens when we start ordering and reordering the different layers. And as you can see here, if you compare the red and the blue spectra, the red spectra is tantalum seed layer, the permalloy is deposited first, and then the BCC nickel 20 iron 80 is deposited second, and the reverse happens in the blue. And what we can see here is that with tantalum as the seed, if we deposit the BCC first, we lose practically all of the signal. So we looked into trying to lattice match the seed with the BCC, and so we chose chromium. And you can see that it does improve the signal. It's still not as strong as the FCC, but it is significantly improved. Now, because of this result, we wanted to look more at the landscape of what else is happening with the multi-layers. And so we decided from here on in to continue depositing the FCC down first and keeping the tantalum seed layer, because that's what we're used to dealing with in terms of these materials. So we looked at varying the layer thickness. We keep the overall thickness of the film constant at 60 nanometers, and we just vary the different layers. And the FMR traces on the left here. The dotted black line is just pure BCC, nickel 20 iron 80, no permalloy added into the structure. And the pure black line is the reverse. It's just a pure permalloy with no BCC into it. And we are getting expected results. We increase the FCC content, we're effectively decreasing the iron content in it, and as a result, we're getting the decreased magnetization that we would expect. But what we didn't expect was the response of the FMR as we vary the thickness. So you can see here in the red curve, so this is 10 nanometers of BCC, or 10 nanometers of FCC. And we are still getting a very strong signal, and it can be argued that it's actually stronger than the pure permalloy altogether. So not only are we having the added benefit of the increased magnetization that we want, but we're also exploiting the significantly increased resonant frequency that the BCC does offer, while still maintaining the strong FMR response. So it's looking good, but what we are currently now doing is we're trying to fine tune this limit a little bit more to see how far we can actually take this FCC thickness down in the film before we lose a signal altogether. Now, this is really early work. As I say, it's a qualitative talk this time around, but at the minute we can see that as little as 2 nanometers of FCC is still giving us a strong FMR response, and we are hitting the 7 gigahertz range. And if we compare it to what we would have had in the permalloy that's normally used, which is about 5 gigahertz, we're effectively getting a 2 gigahertz increase by a relatively simple structure. So we're now looking further into the application of this sort of 2 nanometer FCC into other materials that we wouldn't normally see a very strong FMR in, such as pure iron or nickel platinum. So, but again, it's current work, and this is what we're doing. But it does look very promising. So just to summarize, and my email is at the bottom there. If anyone wants to contact me, I'd be more than happy to chat further about this or answer any questions. But really, what we're doing at the minute is we've really shown that the FCC monolayers of permalloy are advantageous for the magnetostriction, but they do have a relatively low magnetization when we compare it to something like the iron-rich nickel iron films. The iron-rich, on the other hand, does have that large magnetization and resonant frequency, but the magnetostriction is offset as a non-zero, and it does produce an FMR. But what we are showing currently is that by combining the two together, we can create an optimized structure for applications that need to function at higher operational frequencies. So that's my talk. I'd be more than happy to answer any questions that anyone has.
May I ask a question?
Yes.
So in your talk, I could understand that the FMR signal increases, but what about damping?
So the damping, we have seen an increase in the damping as we apply more of that BCC. And in actual fact, we can see here that the signals are the line broadening of the signals is
that
greater.
I can see the line is broadened quite high for especially this red red curve.
Yeah, but bear in mind that would be 50 nanometers of BCC and only 10 nanometers, so it's a BCC dominant. And we've already seen in the single layers that the damping does increase significantly. If we do actually scale this graph up, we can get a damping value of that, which is significantly larger than what we would expect for something like permalloy.
Yeah, so I'm inquisitive about this. Like, if you really increase your FMR signal with this kind of bilayer structure, then are you losing the sharpness?
We are losing sharpness.
Then is that very much applicable for high frequency application if you have a very broad FMR?
Well, for our particular application, for the reader shields and hard drives, what we want to be able to do is absorb at multiple frequencies. So effectively, we're talking about a broadband filter here. So by having an increased damping, it's not necessarily a bad thing, because we are going to be absorbing at a larger range of frequencies, provided, of course, that we can still get an absorption if you look at the red.
That means you mean to say, if you are having a filter application and then the error limit, so if I see the line width as the error limit, what it can filter according to, so then you are not very sensitive to that, right? And if it is not the case and the higher magnetization is only the priority, then why don't you go for cobalt iron, because it gives you higher magnetization? Well,
that is a very good question. I think the ethos behind our choice of nickel iron was really the I'm going to say the degrees of freedom that we could see. At the end of the day, for our purposes, our applications, we don't necessarily need as high a magnetization as what is in cobalt iron, but we would like to see the magnetization raised a lot more than around 1 Tesla that we would get for nickel iron. So it was more an application choice that, you know, we don't need it as large as the sort of 2 Tesla mark, but we do want it a little bit higher than the 1. That was really the ethos behind our decision for nickel iron over cobalt iron.
Okay, thanks for your
Thank
talk.
you. Thank you.
So there's a question also.
Hello.
Hello.
Yes, my question is, I can can you please tell me about the second mode? Because I can see there is 2 modes. One is the principal mode and the other is the second mode because of the thickness when you are about 100 nano. So you have the second mode. And what about the change in this mode when you vary these different thick materials?
So do you mean the spin wave?
Yes. Can you go in the next slide? I think so. I can.
This slide.
Yeah, near to 11 gigahertz, 10 gigahertz, there is another mode.
Yeah, so that's just the standard spin wave. So I can tell you something about it, but I have to be honest that where this work is concerned at the minute, we're more keen to look at the absorption in the FMR than the spin wave mode. But the longer that we go with this work, the more that we probe into it. As I say, this is early work, so there's definitely something happening by just adding something like 2 nanometers. So the spin wave will probably need to be looked into, but at the moment I can't really comment on the different modes.
Yeah, I can see that the first mode have the change in the intensity, sharpness, but when I look to the spin wave mode, don't have these things.
Yeah.
So I would like to know, maybe you are wondering about this, why this is not behaving like that.
Well, we did actually, this was something that we did wonder. Why are we not necessarily getting the spin wave when there's no permalloy at it, and then when we add 2 nanometers, we're all of a sudden getting it. And as you have very rightly pointed out, the amplitude doesn't change, whereas the FMR peak does. So we are going to be looking into this. At the moment, I can't really comment on it. Other than, yes, I do agree, there is something different happening in the spin wave than what there is on the FMR peak.
Yeah, maybe interesting to investigate this.
Yeah.
Okay, and another question is just quick comment. I don't want to get a lot of time. If you put the 20/80 in the bottom and the 80/20 on the top, and what will be happen?
So this is where
just switch the compositions.
Yeah, so this is where this layer order comes in. So effectively what you're doing is you said that let's switch the compositions around. So this is what this blue curve actually looks like. So when we switch the compositions around, we are getting a completely different FMR response. But again, that we've sort of concluded that that's something to do with the lattice mismatch between the seed and the nickel iron film, because when we do start putting in a BCC seed layer like chromium, we are getting that signal back, just it's still not as good as what it would be when we had the 20/80 on, or the 80/20 in the bottom. But we are concluding that it is something to do with lattice mismatch between seed and the layer that's deposited first. And
maybe it's interesting if you put in the transmission electron microscopy and look the interface.
Yes, that is something that's on a priority list within the next few weeks, just to see what's happening with the layers, how they're growing, what they're going to look like.
Yeah, thank you. Thank you very
Thank
much.
you. Thank you for your question.